Okay, so here are acid-base titrations, and we're going to be here for a few days. So we have done titrations before. You guys did a Explore Learning Gizmo on it, and we did an acid-base titration with that acetic acid way back in the beginning of the year. So we're going to run through sort of the easier aspects of titration and work up to the harder aspects of it. So what a titration is usually a process that is done to find the concentration of an unknown solution by finding how many moles of one thing reacts with moles of another thing. And then you can figure out moles and you already know the volume. So that's how you would find the concentration. So the first type of titration that we're going to do is the strong acid, strong base titration. These are the easiest to do. And really the mathematics behind it is mathematics from last year. Stoichiometry, basically. So a couple of things that you should know about the characteristics of a strong acid, strong base titration curve. First of all, if you're starting with a strong acid, you would expect that your pH would start really low, usually below 2. And the particulate diagram down below shows you what you would start with. The H's and the Cl's, this is actually incorrect. This particulate model is actually a little incorrect. The green is always used to symbolize the Cl minus. So this is actually Cl minus, and this guy is the H plus. It's correct everywhere else. So we start out with just HCl, and it's a strong acid, so it's fully dissociated. You see that those two are not together. Then we start adding base. So that's what the x-axis is, milliliters of base added. And you can see as we add base, the pH starts increasing. But every time that I add base, it reacts with some acid. And what all that means is that we have a little bit less acid, a little bit less acid. So you can see that the pH kind of creeps up. Then really quickly, we will see that it spikes, because that's when I turned from having more acid than base to more base than acid. And where you will see straight up and down will, for a strong acid, strong base titration, will always be at a pH of 7. And that is what we call the equivalence point. The equivalence point is where the moles of H plus are equal to the moles of OH minus, which means that there's not an excess of H plus, there's not an excess of OH minus. You would take the pH, or the H plus concentration, is the same as neutral water. 1.00 times 10 to the negative 7. pH is a pH of 7. And then after we go beyond the equivalence point, we can see that now we're adding an excess of OH minus. So the pH there is quite basic, and we will see like up around 12 or so. So the hallmarks of a strong acid, strong base titration are twofold. Number one is the equivalence point being at a pH of 7. That won't happen when we have a weak base or a weak acid. And the other one is going to be the starting out low and then being a really smaller slope right up until the equivalence point. What we'll notice when we have a weak acid, strong base, is that it will be a little bit more with a higher slope there. Okay, so those are sort of the differences between the two. So now, first thing we're going to do is write the chemical equations and then do some math for it. So the first part here, write the balanced chemical equation and the net ionic equation for the following neutralization reactions. Aqueous acetic acid is neutralized by aqueous barium hydroxide. So anytime that you have a weak acid, we do still keep it together when writing out a complete ionic and net ionic equation. So acetic acid is, of course, CH3COOH, and barium hydroxide is BaOH2. Now that is strong, right? These are both aqueous. And what will happen? Well, of course, the H and the OH will get together to form water. and the other product will be barium acetate. And now we need to crisscross the charges, actually figure out what is the charge of, or what is the formula of that other product, barium acetate. And then from this, we need to balance it, noticing that there's 2 acetates on the right. So I'm going to need 2 moles of that acetic acid on the left and 2 moles of water. You can remember that we can rewrite water as HOH, right? And this can remind us that, yeah, we're going to need 2 of them, because we're going to need 2 for the hydroxide and then 2 for the hydrogen off of the acetic acid. So that's the complete balanced chemical equation. In order to write the net ionic equation, which is what the question asks us, that means breaking up anything that is aqueous on both sides. Sorry, this guy is aqueous over here. And water is, of course, a liquid. So I don't dissociate weak acids. So this will still be 2 CH3COOH. And now I can look on both sides and see that barium is in an aqueous substance on both sides. So barium is one of the spectator ions. Barium is, of course, barium hydroxide is one of the strong bases. So I know it completely dissociates. Barium is a spectator ion in this case. So I can just add the 2 hydroxide ions. It will make 2 water molecules and 2 acetate ions. And then you could, excuse me for the 2, and then you could simplify it by just doing 1, 1, 1, and 1. The next one, solid chromium hydroxide, chromium 3 hydroxide reacts with nitrous acid. So solid chromium 3 hydroxide is CrOH3. And if it tells us solid, it tells us solid, which means we're not going to dissociate. Nitrous acid, on the AP test, you're not expected to know the names of compounds like that. So they would tell you it's HNO2, and that is a weak acid. And that will, of course, the positive of one hooks up with the negative of the other, H plus and OH minus. So we're going to make liquid water, and the positive ion of one hooks up with the negative of the ion of the other. So that will still be chromium 3 nitrite. And now I have to balance this. I can notice, remember, we can cross this out and make this HOH, and then notice that I have 3 hydroxide on the left. I would have to put a 3 here to make 3 hydroxide on the right. I can also tell I'm going to need to put a 3 there to give me 3 hydrogen, not in hydroxide. Sometimes I like to, color code those, like this guy and that guy would be that hydrogen. And also the 3 nitrite ions. So now I can write the net ionic equation, but remember, I'm actually not going to dissociate all that much in here. Solid chromium hydroxide, it tells me it's solid, so I am not dissociating that. Weak acids, I don't dissociate. Right? Liquids, I don't dissociate that. So H2O or HOH, it really doesn't matter. Chromium nitrite. If we take that chromium nitrate is soluble, which I'm pretty sure it is, then I could just dissociate that into Cr3 plus aqueous plus 3 nitrite ions, also aqueous, but I don't get to cancel anything out. No spectator ions here.